Hello, this is Mr. Huber. In this lesson, we're going to look at graphing rational functions. Remember, a rational function is something that can be written as a fraction. So in this case, we're seeing the fraction in this equation, this function, is going to be written as a polynomial over a polynomial. These are other functions, right? P of x and q of x. These are some polynomial functions, right? First, let's talk about domain. Remember, domain is all of the inputs, okay? Most of the time, we talk about that being an x. Well, we want to make sure that we don't plug in numbers that make the denominator equal to 0. So the domain is all real numbers except anything that will make the denominator equal to 0. So if, for instance, we had a function where the denominator, okay, we just have p of x, we're not worried about the numerator, but if the denominator was x minus 5 and x plus 2, okay, we would want to make sure that we didn't have any x values that would have x minus 5 equal to 0 or x plus 2 equal to 0. Because if I plug those in, I'll get denominators of 0 if I put in a 5, or here if I subtract 2 on both sides and get negative 2. So we'd say our domain is all real numbers except x equals 5 and x equals negative 2. Okay, we'll see some more examples as we go forward, but just keep in mind that's what it means. We don't want a denominator equal to 0. We can't have the domain where that's possible. We also want to look at those as discontinuities, okay? The graph is going to be called discontinuous where the denominator is 0. It means it doesn't continue. It goes to a point, but it can't include that point, so it doesn't continue, in this case, at x equals 5 or x equals negative 2. So there's some different things that can happen at those points of discontinuity, okay? If p of x and q of x have a common factor, so if in the numerator here there was also x minus 5 as one of the factors, so there's a common factor, then the discontinuity is removable, and we just draw an open circle on the graph at that point. Okay? If it's not a common factor, so if there wasn't an x minus 5, let's say in the numerator, so this x equals 5 was only making the denominator equal to 0, then we have something called a vertical asymptote. Okay, an asymptote, remember, is a line, a boundary on a graph that the graph will approach but never reach. Okay? We'll see some examples of these. So we want to make sure that we know what those discontinuities are and how to draw them in on our graphs. Horizontal asymptotes. So vertical asymptote here, this vertical is something going up and down, vertical. A horizontal asymptote will be a horizontal line boundary on a graph that the graph will approach but never reach. How do we know where theirs are? There's 3 situations we want to test. Okay, m and n are degrees of the numerator and denominator. So that would be, for instance, if we had x squared plus 5x minus 3 over x plus 7. Okay? So the degree of the numerator is 2. In this case, the m, the degree of the numerator would be 2, and the degree of the denominator, n, would be 1. Or the degree of the numerator is the highest exponent, the exponent of the leading term. Okay? So in this case, m would be 2 and n would be 1. So we'd look down here and see, oh, m is greater than n, there's no horizontal asymptote. If m was less than n, we have a horizontal asymptote at y equals 0. And if m and n are equal, the horizontal asymptote is at y equals a over b, where a is the coefficient in front of the numerator and b is the leading coefficient of the denominator. So if it was this case, if m and n were equal, if I put it as squared in there, if I added a squared in there, so now m and n are equal, then the horizontal asymptote would be at a over b, would be at 1 over 1. So make sure we understand these different features of the graphs and how we can find discontinuities, places where we can't have a number that's part of our domain that might be an asymptote vertically, and then how to find our horizontal asymptotes. And we're going to go through some of these and see some various examples of them in the coming examples for you to work out along with me. All right, so now let's look at some examples. We want to find any points of discontinuity. So let's just start there, figure out what does that mean. So this means we want to figure out where our denominator would be equal to 0. So we want to set x squared minus 4x plus 3 equals 0, and we're going to have to factor it. Okay, so we can factor this to x minus 3 and x minus 1, and we want to set it equal to 0. So x minus 3 equals 0, and x minus 1 equals 0, means x equals 3 and x equals 1 are my points of discontinuity. So we factored the denominator, because we want to see what numbers I would plug into here to make this equal to 0. So if you put a 3 in here in the denominator, it's going to come out to 0. 3 squared is 9, minus 4 times 3, that's 12. 9 minus 12 is negative 3, plus 3 is 0. So we have a denominator of 0. You can't plug in a number that will give you a denominator equal to 0. Okay? And it doesn't have a common factor. X minus 3 and x minus 1 are not common factors. X plus 3 and x minus 3 are not the same factor. So therefore, these discontinuities are non-removable. There would be vertical asymptotes at our graph at x equals 3 and x equals 1. When we get to graphing, we're not going to do that right now, but we will in an example a little bit. We'd go to 1 and 3, and we'd have a vertical asymptote at 1 and at 3. Those would be boundaries our graph will approach but never reach. All right? And we're going to see what that looks like in some coming examples as well. So our domain for this, to get back to our question, right, it says state the domain. Right, the domain is all the numbers except those which we would plug in and make the denominator equal to 0. So our domain is all real numbers, okay, except, I'm going to erase the graph here so I can write the answer for the domain part, all real numbers except x equals 1 and x equals 3. And we'd write it out just like that. So it's all real numbers except x equals 1, x equals 3. All right? So that's our domain. We get that, again, by figuring out where our denominator would be equal to 0. In our second example, all right, the numerator isn't factored, but we need to factor it, not to figure out where the zeros are, but to see if there's a common factor with the denominator. So in our numerator here, we would factor this to x minus 4 and x plus 1. And if you need help with factoring, let's make sure we're practicing it. You can see where we're going to need to use it in these examples. So x minus 4 is a factor in the numerator and denominator. So when we get our x equals 4, because we want to figure out where our denominator is equal to 0, x minus 4 equals 0 will give me an x value of 4 that will make the denominator equal to 0. So this is a point of discontinuity. Okay? Since it's a common factor in the numerator and denominator, it's going to look like a hole in the graph. Let's talk about that here in a second, but first let's write out our domain, which is all real numbers except x equals 4. Okay? And so when you go to draw this graph, this is not what the graph necessarily looks like, but let's say it looked something like this. Okay? If 1, 2, 3, 4, at the point x equals 4 right here, we'd have an open circle. Okay? Because the graph is discontinuous at that point. It goes up to 4 on both sides, but it won't actually have a value of 4 because if I put in a value of 4, I'd have a denominator of 0. So that's what that looks like on a graph. Point of discontinuity, okay, where it's a common factor in the numerator and denominator, is going to be an open circle. We saw over here those were asymptotes, those vertical lines that the graph will approach and never reach. So let's talk some more about vertical asymptotes and horizontal asymptotes. So number 3 asks us to find the vertical asymptotes. So in this case, we want to figure out what numbers will make our denominator equal to 0, because there's not a common factor. So we just need to figure out where our denominator would be equal to 0. Okay? So our vertical asymptotes are going to be at x equals 3 and x equals 2. And on a graph, what that would look like is that 1, 2, 3, is that x equals 2, a vertical line. At x equals 3, a vertical line. And then the graph that goes around it would approach that and never reach it. So let's say maybe it looks something like this. It would be coming close to that asymptote but never reach it. Again, I don't know if that's what the graph this looks like. I'm just reminding you what it means to be an asymptote, where the graph approaches that boundary but never reaches it. Right? And we find those by figuring out where our denominator is equal to 0. Now for the horizontal asymptotes. This is where we want to look at the degree of the numerator and denominator. Okay, here this is a degree 1 and degree 1. Okay, this is a situation where we say m equals n, right? The degree in the numerator and the degree in the denominator are equal. So when that's the case, we have y equals a over b for our horizontal asymptote. And the a and the b are the leading coefficient in the numerator and leading coefficient in the denominator. 2 over 1. There's no number in there, so it's a 1. So we would have y equals 2 as a horizontal asymptote. And that'd be a dashed line going across the graph. Like if this is at 2, we'd have a dashed line going across here at y equals 2. So y equals horizontal line, x equals vertical line. Vertical asymptotes, horizontal asymptote. Now we come over to number 5, we're going to have to factor that denominator, because we want to be able to figure out where it's equal to 0. So that's going to be x minus 3 and x plus 1. Okay. Negative 3 times 1 gives me negative 3. Negative 3 plus 1 gives me negative 2. Right? And so I look here, those would be my vertical asymptotes. Okay? Just as a reminder on the factoring. Now talking about the horizontal asymptotes, we don't have to worry about the factoring there. We just want to look at the numerator and denominator and the degree of the leading coefficient. So here m is 1 and n is 2. So we have m less than n. When m is less than n, we have a horizontal asymptote at y equals 0 every time. And in the next example, we have m greater than n, because the degree of the numerator is 2 and denominator is 1. And so there's no horizontal asymptote. I'll just abbreviate that. No horizontal asymptote. Okay? So when the degree in the numerator bigger than the degree in the denominator, no horizontal asymptote. All right, so a lot of things going on there. We've got mostly to do with finding where our denominator is equal to 0. So we have points of discontinuity, vertical asymptotes, numbers that can't be a part of our domain, and then horizontal asymptotes. So we got to have those key parts of our graph so that we can draw the graph accurately. All right, and we're going to be getting to that here very shortly. But first, I'll laugh out loud. What is black, white, green, and bumpy? Black, white, green, and bumpy. Well, obviously a pickle wearing a tuxedo. All right. And the next one, what did the apple pie say to the pecan pie? You're nuts. Okay, you're nuts. So another terrible joke here would be what the best thing to put into a pie is. So what would be the best thing, do you think, to put into a pie? And no, I'm not going to say bacon. It's your teeth. You got to put your teeth into that pie so you can eat it up. All right, I'm a purveyor of terrible, bad, lame dad jokes, and those are a couple that come to the top of my mind. So there you go. A little humor here before we're graphing rational functions. All right, so for graphing these rational functions, we will first want to draw in asymptotes, and then we want to plot some points around the asymptotes, including intercepts and other key points. So we're going to look at this graph here. It's going to have a lot going on to it, so make sure you're paying attention to how we're getting all these different parts, the vertical asymptotes, the horizontal asymptotes, and then how we can draw in some points. Okay, and it might take a little while, but as you get used to it, it'll come a little more quickly. The first thing we're going to have to do is factor this, because that's how we're going to be able to know if we have common factors, where we're going to have denominators equal to 0, okay, things like that. So we're going to have the numerator is x plus 4 and x minus 3. 4 and negative 3 multiply to give you negative 12 and add up to positive 1. And the next one's a difference of squares. Difference of squares is where I'd have a difference here. We're subtracting two perfect squares. The square root of x squared is x and x. The square root of 4 is the 2 and the 2. 1 plus and 1 minus. Okay, so that's one of those special factoring patterns we want to remember and be aware of. Okay, so we see here the factored form, and that's going to help us figure out where we have asymptotes. So let's talk about the vertical asymptotes. Okay, vertical asymptotes are going to be at x equals negative 2 and x equals 2. Set those two factors in the denominator equal to 0. So let's draw those in here. So we're going to have at x equals negative 2 and x equals 2 vertical asymptotes. Horizontal asymptotes, and this is where we go to m and n are equal to each other. Since m and n are equal to each other, there is a horizontal asymptote, and it would be at 1 over 1, where we take the leading coefficient over leading coefficient. So we're going to have a horizontal asymptote at y equals 1. So that's going to be across the graph like this. Now to draw our graph, we want to find some points over here to the left of this asymptote. We're going to find some points in between the asymptotes and then some on the right of it. So we're going to make a table of values with a few different sets of points. It might be a relatively large table of values. So we're going to have x and y. And first let's pick some points over here. So if this is at negative 2, we might want to plug in negative 3, negative 4, negative 5. Okay? So I'm going to plug in negative 5, negative 4, negative 3. We're going to go back to our original equation here. We're going to plug those numbers in. Again, with your calculator, you do negative 5, put it in parentheses when you square it, so you get a positive 25, minus 5, minus 12, and then negative 5 squared minus 4 in your denominator. You're going to put all that in, you're going to get 8 over 21. Okay, 8 over 21. If you have it as a decimal, that's fine. I'm going to write it as the fraction, 8 over 21. Just make sure we know where to graph that. You plug in a -4, and you're going to get 0. You plug in -3, and you should get -6 over 5. Okay? So now when I go to graph those points, I'm going to go to -5, and then 8 over 21, so that's right around there, a little less than half. -4, comma 0 right there, and then -3 and -6/5 is a little lower on the graph than -1. So I'm going to have this part of my graph going like this. Again, approaching the asymptotes, but not reaching it. Don't cross the dashed lines. Do not cross the dashed lines. Okay? Then we're going to find some points here in the middle. So we need to plug in some points between the asymptotes. So -1, 0, and 1 will be nice numbers to plug in there. So I'm going to plug in -1, 0, and 1. When I do that, I'll get 4, 3, and 10/3. Again, you want to practice making sure you can plug those in and things work out. Okay, that's just knowing how to plug numbers in for x. So I'm going to have -1, comma 4 right here. I'm going to have 0, comma 3. That'll be right there. And then 1, comma 10/3. So that's 3 1/3. So 3 1/3, a little bit above 3. So I'm going to have a graph in the middle part here that goes like this through those points, and again is going to approach those asymptotes but not reach it. And then we need some points to the right of the x equals 2 asymptotes. We need some points over here, so I'm going to try 3, 4, and 5. So let's plug in 3, 4, and 5. And don't just go up to the top and go, oh, and I plugged in -3, I got this, so now I'm going to plug in 3 and get, the same type of thing. It's not going to work. They don't just change signs there. So I'm going to plug in 3 and get 0. I plug in a 4, and I'm going to get 2/3. And I plug in a 5, and I get 18 over 21. Again, if you have those as decimals, it's fine. So 3, comma 0 is right there. 4, comma 2/3. So 2/3. And 5, comma 18 over 21. That's really close to 1. So we're getting closer and closer to that asymptote, but we're not going to reach it. We're going to approach it, and we're going to have a graph that looks like this. Okay. So there's your graph. Again, let's back up here and talk about how we started this. We got our asymptotes. Okay? Graph your asymptotes in. -2 and +2 for the vertical asymptotes. Horizontal asymptote. Degrees the same, so we put 1 over 1. 1 over 1, that's y equals 1. Draw in those lines. X equals -2, x equals 2, y equals 1. And then find some x values on either side of the asymptote here, out here, and then in between. And you're just going to have to make a table of values. And when you make that table, then you got some points you can draw your graph in, make sure you're not crossing asymptotes, and you get a sense for what that looks like. If you want to plug in more than 3 points around those different areas, just to make sure you got a good sense for it, that's fine. Okay, you can do that. You can plug in as many as you want. All right, let's look at one more graph. And this one's not as complicated. I went through about as much as you're going to see. That last one's got pretty much everything you see. Vertical asymptotes, horizontal asymptotes. This one's got one other little different thing that we do want to bring up. It's got one of those points of discontinuity that's going to be a hole in the graph. So make sure you're looking for that and knowing how to work with it. Okay, so let's start by factoring here. This first numerator, I can factor out a 3. Don't forget about taking out common factors. I can factor out a 3. And then now I got another difference of squares, x plus 1 and x minus 1. So when I look at my x values, I'm going to have x equals -1 and x equals 1 for my points of discontinuity down here. Since this is a common factor, the 1 is not a vertical asymptote. It's a hole in the graph. I'll write that down. This is going to be a hole because it's got the same factor in the numerator and denominator. Okay? X equals -1 is going to be a vertical asymptote. Okay? And then we look horizontal asymptotes. We've got the numerator less than the denominator. Okay, so m is less than n. We're going to have a horizontal asymptote at y equals 0. Y equals 0. That's right here on the axis. All right, that's on the x-axis, y equals 0. So now again, I want to make a table of values so that I've got some points that I can plug in. So I'm going to put some x's, some y's. I got to go on either side of my asymptote there. So I'm going to plug in for that x values of -4, -3, and -2. I'm going to get -1, -3 halves, and negative 3. And then on the other side of my answer, I'm going to plug in 0, 2, and 3. Why didn't I pick 1? Well, I didn't pick 1 because when I plug 1 in here, I'm going to get a denominator of 0. That's a point of discontinuity. I'm going to have a hole in my graph where that comes in. Okay? So now when I plug in these points, 0, I'm going to get 3. I plug a 2 in, I get 1, and 3, I get 3/4. So I'm going to graph these points. Negative 4, comma negative 1. Right here. Negative 3, comma negative 3/2. That's negative 1.5. And negative 2, comma negative 3. Right around there. So again, I'm going to draw my curve in through these points. And I'm going to make sure that I don't cross any asymptotes. And I should be good to go. Then I'm going to plug in 0, comma 3. 2, comma 1. And 3, comma 3/4. And we're going to have a graph that goes like this. And when I get to here, right, I want to come back to that. Okay, no, don't cross that. I kind of slid my graph over there a little bit too far. I'll try to erase that. And we'll bring that up a little more vertically here so it doesn't cross our asymptote. And I want to go back now and talk about that hole in the graph. X equals 1 is going to be a hole. So where x equals 1, wherever I have that on my graph, the x equals 1, I'm going to go back, and you can erase if you want a little bit. You don't necessarily have to, as long as you make sure there's a circle there that you can make sure is clear that you're drawing in as a circle. Okay? You're going to have an open circle at x equals 1. And our graph connects to it on both sides. So that's a point of discontinuity. That's not an asymptote, but we can't have an x value of 1. You can plug in numbers on either side of it. You can plug in all these x values. You can plug in all these x values. But when you plug in a 1, you'd get a denominator of 0. You can't have that for your function. So the graph can't exist at x equals 1, even though it does on both sides of it. Okay? Let's talk about the domain and range. Okay? For the domain and range here, all right, in this problem, the domain is all real numbers except negative 1 and 1, just like we saw before. So the domain is all real numbers except x equals negative 1, x equals 1, right? Those are our holes in the graph. The y can be anything except 0. So the domain here, okay, the range, right down here, is all real numbers except y equals 0. Right? I can have any y value I want. Y values here go down forever, and they come all the way up except not to 0. And then above 0, they go up forever. Okay, so we want to make sure we identify domain as everything that you can have as an x value, and the range is everything you can have as a y value. So basically, we're looking for what can we not have. We have all real numbers except certain x and y values. So a lot going on there. Again, that first slide goes through a lot of this information. You may want to have that. Again, print it out from the notes. Do what you need to make sure you're going through, you're understanding how to work with these different parts of these rational functions, identifying key features, and then using those in terms of drawing our graphs.